Thank you so much. All right, welcome everybody. It is ASAN seminar session number 6, and I'm happy to be able to bring this session along with Vishnupriya Varadaraju and Professor Mala Nehru. Vishnupriya is a CEG alum from EC department in 2020, very recently. And Professor Mala Nehru is from the IST, Information Science and Technology Department. Vishnupriya, could you maybe say a few words about yourself?
Right. Thank you, Karthik. So, hey everyone, my name is Vishnupriya, and as he mentioned, I'm a very recent alum from CEG. So I passed out from the EC department in the year 2020. So it's also called as a COVID batch. And currently I'm pursuing my master's in computer science at the University of Massachusetts Amherst. So I'm doing a concentration in data science because I'm interested in that field. And before this, I was working for about a year and a half at a company called Fortinet, where I was working as a software development engineer. So that's pretty much my background. And I'm really happy to see all of you in this session today. And thank you very much for joining. Yeah. Thank you, Karthik.
Thank you. Sorry about the slide running away. Let me go back to it. In this, I think we have good strength. Thank you, Vishnupriya. So the topic of today is a little bit of a mix of two things. I'll be talking a little bit about myself and sharing some stories from my life that I believe may be helpful for the students, and also talk about on a topic of my experience, which is on computing, and what trends do we see from that standpoint. So a little bit of to get warmed up. I shared some of this during the first session, but really wanted to spend a few more minutes, maybe get some input from students. So my academic journey, elementary and middle schools, are from two schools called Vivekananda Vidyalaya in Chennai. They have several schools actually. And then from Madurai, a school called as TVS School or TVS Lakshmi School. Anybody here from any of these schools or from Madurai or anything like that? Could you share a little bit, maybe even very simply, how many of your day scholars and hostlers? Can you maybe say something in the chat if you're a day scholar or a hostler? Don't worry. There are some messages already. Good. Day scholar. We have one day scholar, I think. A few day scholars. We know one hostler and one day scholar from the previous responses. Day scholar. All right. So we have many day scholars, and maybe if I have to assume the sample is random, then a few hostlers. I was a hostler in CEG, and right after high school, all through elementary, middle, high school, or middle and high school, science and mathematics was most fun. I think most of us probably share that interest. And so but at the point when I came to CEG, it was all very interesting in that I took computer science in CEG, but I had not known anything about computers before doing that. Somebody, actually, I'd even not learned about what Anna University or CEG was. I think towards the final few months of 12th grade, somebody told me that, oh, this is a very prestigious institution, and that if we get a job here, or if we get a seat here, they would you can get a job for 10,000 rupees. I think that was my main motto. Oh, get a seat here so that there is a job for 10,000 rupees. And so it was really the first year or so of college. It was all like, okay, I've done all the studying to be done in 12th standard. There is no more studying to be done in life. That was the feeling that was there. And the boy, was that wrong. There was getting introduced to the professors, the students. It was all a really amazing experience. Some of the most important personalities, teachers that I'm very grateful for, that I have personal connections even today. Those 4 years are the reasons for it. Another student had asked why, in one of your assignments, why I spent some time with CEG. It's mainly that I've gained so much from it, and I'm really grateful for it. So many friends that we maintain connections to date are from CEG. I've also been fortunate to do that in from school as well. But really very grateful for CEG. And I mean, right after the first year, or towards the end of first year, it was clear that the field was an ocean, and that I couldn't get enough of it. There was the professors and my friends and colleagues were so fun and inspiring that I wanted to really study. Wanted to study. A PhD was the interest, and always it was about wanted to really know what is under the hood. I mean, if you're, you may think as having been introduced to engineering, we always wanted to know what is underneath something. How does this work, or how does that work? Can you try and understand what's happening inside? That was the interest, really, and that naturally led to interest in computer architecture, or basically how a processor or chips inside computers work. That became my interest, and naturally that was how all the graduate school interests came about. So I went to University of Virginia for grad school, where I studied computer architecture as the area of specialization. And a couple of internships in the industry really helped me understand even my own dissertation better. And after when it was time to graduate, I'd worked on a problem for a dissertation, but that was reasonably not too big. So I'd converted it to a master's and then started on another problem. What problem it is, I'll talk about it briefly. But I joined Intel right after grad school. So that's where I've been for the past 12, 13 years. And in terms of what my experience has been, what my area of focus has been, it is in CPU microarchitecture, or essentially how, in simple words, it's understanding and building CPUs, how they work, how do you make them work faster, cooler, quieter, more energy efficient, so that it lasts for a long time with little bit of a battery. These are the main focus areas. So I mentioned making them run in a very energy efficient fashion with little battery, and then cooler and quieter. The technical words for those are power or power aware design, or thermal aware design, or acoustics aware design. What about it is quiet? If you may ask, it is your laptops or desktops and so on, they have fans and they may make noise, or there are some other kinds of noise due to when a computer goes to sleep and wakes up very often. So these kinds of physical problems are some focus areas that I've worked on. Another, usually the software person for hardware team members, And then the hardware person for software team members. I'm usually at the borderline between hardware and software. Another topic that's that have been of interest is what are called as dynamic compilers. Don't worry if you don't, the words don't make sense. It's essentially programs that run other programs. So your Python interpreter or JavaScript and engine and so on, they run other programs. They run your Python program or Java programs. So these dynamic compilers are programs like that. And I was, for a little bit, I was looking at those kinds of programs and trying to understand how you can improve them. And more recently, it's about, as you can see, as a processor company that makes CPUs at Intel, we really care a lot about making our hardware work really closely with the software. So that's the focus. How do you make it work so closely with software? How do you optimize the software or workloads to our interest? Is essentially some of the focus areas that I've been working on. So at this point, I want to stop and ask if there is any questions. Do you have any questions for me? Any of these words, do they ring a bell, or do they not make sense? Please feel free to, unmute and talk. That's fine too. It would be great to hear some of your voices, or put it in chat. No problem. All right. So the agenda, with this background, the agenda for today is really twofold. On the first part, I'm going to share a few stories from my life that I believe could be helpful. And on the second part, we will talk a little bit about computing and technology, maybe take a very high level, so not to be scared if to see if we go into too many details. No, this is going to be decidedly a reasonably high level talk. All right, so let's begin. 3 anecdotes, 3 stories from different times of life. The first one, was there a question? Somebody, I thought somebody unmuted. Feel free to stop me, all right? Okay, this anecdote, I've titled this as saying the race is with oneself, really, is the timeline is really at transitioning from high school to CEG. There was this time where, I had studied biology and mathematics and physics in 12th standard. So, I'd applied to both medicine and engineering. And at home, my mom and family members, there has never been a doctor in the family before. So there was a lot of interest. They were really, if I would get admission in medicine, they were really eager. They were eager to see that happen. But I was personally, I liked science, I liked biology too, but really loved mathematics. So I did not want to miss mathematics at all. Plus, I was not so good with reading large books and memorizing a lot of information. That was not my strength. So I was really hoping that I would be able to take engineering. I would be able to go to CEG. But seeing that the family and actually even friends, not just family but family friends, there was one of them was a doctor in Madurai Medical, and he was he would actually pray to there is a temple in near Madurai called Tirupurangundram. So he would pray to the Lord, and he would walk. We used to live maybe several kilometers away from the temple. He used to walk as prayers for the God, thinking that, oh, if I get admission into medicine, then he would pray to the God. And on seeing this, I was really moved, and I thought, oh, so many people are eager. Am I really dashing their dreams or spoiling their dreams? Was the thought. And on that day, I talked to my mom, asking her, so do you think then I should probably take medicine, Amma? And the answer that she gave me has essentially stayed with me, and it's been very helpful. So that's the first anecdote that I wanted to share you with, which is that she said, "See, yes, I would love for you to study medicine, and it would be great to be able to say that, but." We will have our dreams or these kinds of interests today, and then we'll move on and we'll start doing our things, whatever our life is. We'll go on with our lives, but it's really you who is going to study, who's going to spend the 5.5 years. In this case, medicine was at that time 4.5 plus 1. Spend the 5.5 years to learn. And so really don't decide for others, decide for yourself. Go for where your heart is, was the advice she gave me. And so true. I'm very thankful for that advice, and it's been the right choice. I mean, anecdotally, of course, she got her wish of a medical doctor in the family through marriage. My wife is a physician. That's a later happening. So it's really, if you the takeaway here for all of us is, see, in any topic, doesn't matter. I mean, success will require a lot of work. There is no question about it. There's nothing called as easy success. That is, because career or life is a very long process. They call it very often that it's a marathon, not a sprint, right? So there is no question that one has to work hard. But if your heart is not in something, then it is not possible to work hard. It would be torture. So it's absolutely important to have our heart in where what our choices are going to be. And I mean, anything like that. So for instance, a PhD advisor is a choice like that, a long term. I mean, you're going to spend the time with the professor 5+ years. Likewise, very important choice. Like all matters of heart, it's better to trust our gut, trust our heart. I mean, same thing. For instance, the choice of a spouse. These are all choice of a career is not very different. These are we're going to remain in it for a very long time. So it's better that our heart lies in that. So that's really the first anecdote that I wanted to share. Any follow-on thoughts before I go to the next one? All right. The second anecdote is from much later. This is after I joined Intel. The first few years, I mean, I'd said no to other companies because I thought I was interested in academics and research. So the opportunity to join Intel Labs, where they were doing everything from, at Intel, you could find a physicist, a material scientist who builds transistors, or all the way up to people experts in software and security. So the complete stack, you could see experts. So that was very attractive. And when I joined, I was all eager. And this, right when I was finishing grad school, it was like there was the I wanted to. I mean, I've been interested in teaching for a while, but at that point, when I had finished PhD, I was not confident enough to guide other students. Plus, also, this was another question from one of the students during the assignments, and also that at that point, U.S. universities looked like they were already very well staffed. I didn't see myself adding much value to the university system here already. So I thought the problems in the industry were very interesting. So joined Intel. So the story takes a very interesting turn in that after about 3 years or 3.5 years, doing, I mean, what I thought was exciting work, doing stuff all the way, I mean, starting with problems for ground up, and then finding solutions, and also pushing those solutions into products, going the full stream from developing technology to deploying technology. All of that as a small group was very attractive. Having doing all that, I was like, oh, this is the dream job. Was the feeling. And one fine morning, what happened was got a call from boss's boss saying that, oh, we're very sorry, we have to shut down this lab. So that was like a wake-up call. So a first layoff for anybody is, I think, an amazing reality check, and that was what happened. It was, and it has turned out that the business realities in an industry, it's not like an academic job where once you get a tenure, the position is permanent. In the industry, anything can happen. And if the business realities change, jobs can go away, and we learn to adapt, essentially. And at Intel, interestingly, this has happened multiple times. This is my fourth job within Intel, but really only one change was sort of voluntary change. So that's, I mean, the decade or 13 years that I've been at Intel, the business challenges that the company has faced and adapted are essentially the reason why these things happen. So the takeaway here for me, why am I sharing this anecdote with you, is there are many things in life that we don't control, but there are most important things, which is ourselves, that we control. So if we end up focusing on things that we don't control, it can be a very unproductive or a um, very painful interaction or a painful feeling. But if we focus on what we control, however small, whatever small thing that is, we can still make progress. And that is what the career at Intel has taught me. Even if I look at it, both challenges and opportunities are just two sides of the same coin. The very fact that the business dynamics have been so varied has also allowed me the time to be able to do even things like these, the time to be able to contribute back to the institution that I've been grateful for, and so on. So that is the second anecdote that I really wanted to share. Focusing on what we control and acting in that way has been very helpful for me. I hope it's helpful for you too. And at this point, do we want to see if there is any thoughts, questions? All right, let's go to the next anecdote. This picture here shows two different ladders, one with very small rungs, where one is the person there, she's able to climb very easily. On the other, the rungs in the ladder are far from one another. They're and then so it's hard to climb. And the story here, the anecdote here, I've titled it saying "Small Measurable Steps Forward." I want to share this anecdote, a more recent one, about 3-4 years ago, where this was about one day where, unfortunately, a manager, one of my first managers at Intel that I respected very much, he actually passed away because of cancer. And it was we were at his memorial service celebrating his life, and there was a video in there that really shook me. And in that video, just I think taken a day or a few days before he passed away, he was sharing his own spiritual journey. So he was in a very convinced manner, in a very motivated fashion, he was sharing some of his spiritual thoughts. Whatever his path was, what was most interesting to me was that, I mean, as they say, he knows that he did not have long to live. And when a person does not have long to live, whatever comes out of them with their words have so much conviction. They have nothing to lose. There is no truer word that can be spoken, is usually what we say, right? And that conviction was what was really impressive for me. This was a stage in life where, of course, having gone through life itself, we have two daughters. There's a lot of job-related issues, and then I mean, as a family. Likewise, my wife, my spouse, also, she has gone through a lot of challenges in her career. This was about practically midlife, and then when I was at this the funeral, the memorial service, it was very clear to me that if I was continuing what I was continuing, um, in my deathbed, it felt like, oh, I would be a very regretful person. This is not the direction that I had that I had planned or dreamed of going, and it was very clear that moment that that was not the right direction. And that it was up to me to change it. So to be specific, it was like, oh, whether it's dropping the children in school, getting angry with the children that we want to love so much, picking maybe fights with the spouse or parents and family members, friends. This was all happening, and it was clear that these are not things that I wanted. I wanted to be kind to the people that I love and who have loved me, and who I'm very grateful for. So there was, on seeing this, I was like, I have a very close friend who is a very experienced meditator. So I'm just using this meditation or as an example. It could be anything in life. One may want to do, maybe run a marathon or get a job or create or pass an entrance exam or find a life partner, whatever it is that we want to do. This was my journey, so I'm just giving you this example, but it could be anything. And I was talking to this friend and telling him, see, on seeing this video from my manager's memorial service, I want to know, what is this meditation business? What is this? I tried some before, but did not really put, or it did not stick. And so this time I told him, see, I want to take the approach that I do at work. I mean, if there's an engineering problem, how I would solve it, same way I want to look at this in a very fundamental way. He said, great, do this, but I'll be happy to answer any questions you have. But really, talking is only one part of it. What or how many minutes per day can you commit, was the question he asked. And I was already, at that point, I was like, oh, I was already overwhelmed. There were too many things that I was juggling at work, in the family, and so on. So I said, I will spare 5 minutes a day, because that's essentially what I thought at that time I could spare. So I said, I'll only spare 5 minutes a day. He said, great, let's practice and see whatever questions you have. And how I would find that 5 minutes, just 5 minutes a day, would be, running around, basically we used to have a long commute, we used to drop the children in a different place. So go drop the children in school and then go to work. And before getting into the building, I would park the vehicle and then delay my getting off the car by a few minutes. So that was the 5 minutes I would take after parking, but before going into the building to work. I would stop, and that's when I started practicing for 5 minutes a day. And then the benefit in that, the calmness that came about, saying that, oh, thankfully that moment of silence with oneself was so helpful that in a week or so, that 5 minutes became 10 minutes. And then over later, it became, I think, longer, 30 minutes. There was a 10-day course that I then went to, where it's like a full boot camp, right? Like 11 hours of meditation a day. You don't talk to anybody, no talking. Two meals a day that is provided by volunteers. So it's no money involved in any of this. It was all a voluntary based thing. So I thought it was a good experience. And since then, now it's been 4 years now. The practice has stuck. We've been able to practice regularly, and not only that, the nice thing is the relationships in the family. My parents, my in-laws, my children, my spouse, friends. everywhere, the relationships have improved. And not only that, with some of the family members, this is also a social activity that we do. This is one more thing that we share, meditating together, for instance. So why am I sharing this anecdote? I mean, meditation is an example that from my life I've given, but it could be anything. Anything that we want to, want to make progress on, that we really want badly. Making these small concerted efforts, small steps, the small steps. The picture shows you, you don't want the first few rungs of the ladder to be unachievable. I don't want to set goals that are impossible. Starting small but sticking with it is really helpful. And forming that habit in whatever it is, whether it's, let's say, you may think, oh, I want to start reading books outside your curriculum, or you may say, oh, I want to start exercising. Whatever it is, these small steps forward have been really helpful. And there is a quotation from a Stanford professor that sticks in mind even today, that a little bit of slope makes up for a lot of y-intercept. What it is wherever you are in the y-intercept to begin with, it doesn't matter really. If we change our slope to be a little steeper, a steeper straight line crosses a shallower straight line, whatever the y-intercept is after a point in time. So small measurable steps forward is what's been very helpful for me. Okay, at this point, I want to pause. These were the 3 anecdotes that I wanted to share. Before we move to the technical topic, I wanted to see if there is any question. We've been awfully quiet.
Yeah. Hi, sir. I'm Abhinand.
Yes. Hi, Abhinand.
So I was just curious as to what exactly motivated you to go ahead and pursue grad school back in those days.
Oh, great question. I really, I mean, after the years in CG, having been exposed to the different topics, I really couldn't get enough. So I really wanted to study more, because whatever at the undergrad level, the first time that you see things, you get as much as you, at least I got only what I could get. I mean, but I really wanted to learn more. I wanted to get to the basics, revisit them, understand things better. So, and the other thing was, I was always interested in teaching or explaining things to friends and so on. So this was one, and it still is in the back of the mind. It is one of the possibilities even now. But that was why I wanted to get into academics. I wanted to teach. I wanted to learn. So, I mean, no better way than learning from experts themselves, people who write textbooks practically, right? So grad school, that was the reason I picked grad school. Of course, if I had not gotten any assistantship or anything like that, I would not have been able to go there. But thankfully, the aid came and so on. So it was possible.
Okay, sir. That's nice to hear.
Thank you, Abhinand. Any other thoughts? All right. So we have about 20 minutes. Let's maybe spend a little bit of time looking at some technical topics this time, and then for the next week, I think maybe we'll finish up, and then depending on how much time we have, we can cover other things. All right. So what are we going to talk about? Is just to give you a perspective on the trends in computing, or history of what's been happening over the last maybe several decades in computing. We hear a lot of names or words such as CPUs, GPUs, or accelerators, or tensor cores, and so on. I want to give a little bit of color on what those are for students. So maybe before we start, can students share which department you're in, or is it computer science or ECE? Can you share in the chat which department you're in? IT, all right. IST, IT. Anyone else? Have you had a computer architecture class? Students, have you had? Okay, so you've had a computer architecture class. Wonderful. So some of the material would be then something that you may have already covered at a basic level, and hopefully this gives you a broader perspective if it's already something that you know. All right. So what did we do in ASAN sessions so far? Professor Gerald shared his life experiences, and he gave a little bit of an introduction to programming and how, in the context of bilingual learning, and how live coding helps to understand programming. Professor Jag introduced neural networks and data analytics. But now in this session, what I wanted to follow on with are take a couple of questions. So we've talked about these programs or software. Where does all the software run? It runs on hardware. It runs on these on the chips that are in our computers or in our phones and in all the devices that we see around us today. So how did another in the context of neural networks have been around since the 1990s. So how did they take off in the past decade? The last 10 years, why did they take off so much? We will look at these questions from the point of view of the computer architecture or the CPU design, basically, or microprocessor design. And that's how we'll structure the rest of the presentation. So let's begin. So why do we study microprocessors? I think the most important reason is that they're fun. I mean, they're fun to study. If you like cars, you want to know how the engine inside the car is and how it works. Same thing. If you like computers or if you enjoy benefiting from computers, then it is natural to ask how it works inside. And at least that's what's been driving me to study microprocessors. So they're really fun. And I mean, clearly they're everywhere around us. I mean, if you look at, your own environment, I mean, you can find your washing machines have microprocessors, your audio systems, your computers, your watches. There are microprocessors everywhere. So they're the brain of every intelligent or a smart system that's around. Anything that you can run programs on, it has a microprocessor sitting inside. So it's so ubiquitous, it's around everywhere. So it's important to study them. And why now? It's because it's a very hot topic. The design of microprocessors is extremely hot now. It's not, the industry is not able to find enough computer architects at all. There is a dearth for talent. Industry is trying to collaborate with institutions, saying, "Oh, you please give us the right or tailor some good computer architecture classes. Please give us students with such skills." So it's a very hot topic now. Why is it hot? The reason is because understanding the hardware and software together and how they work is becoming unavoidable to building efficient systems. Previously, it wasn't the case. You did not have to understand this, both the software and the hardware very well. Practically, you could get some of the performance improvements for free. Circuit designers and electrical engineers would give performance improvements that came for free from the architect's point of view, and vice versa. So it's that kind of isolated approach is not giving benefits anymore. So for innovation to continue, it's important to understand microprocessors. So that's why we study microprocessors. what we learned today, I think maybe we will not have time to cover all of it today. So maybe we'll just stop at the middle of what we are thinking about. But what we learned today is, what is a microprocessor? What is a microprocessor? How is a microprocessor made? Both designed and manufactured. How is it designed? How is it manufactured? What are some of the key types of microprocessors? We hear, oh, I have this, my Android phone has so many microprocessors inside. What are a few types of them? And we briefly touched on it. Why is it a hot topic today? And what are some resources to learn more? So that's really the structure of the remaining topic that I had planned. But we may not have time to cover all of this, but we'll stop somewhere in the middle, depending on how far we get to. Okay, before we go to the next step, do we have any questions or thoughts? Do you guys think microprocessors are interesting? They're boring, at least from whatever experiences that you've had so far? Any thoughts? All right. So we'll take in covering this topic, we'll take both a top-down view as well as a bottom-up view. We'll take a top-down view of the world from software, and we'll take a bottom-up view of the chips, looking at it from the point of view of hardware. So we'll take both a top-down view and a bottom-up view. The first thing that we'll think about is what is called as an instruction set. What it is, some of you may already know, some may not. The picture on the left side is essentially a program written in C. It just prints hello world and a number for 500 times. So it prints hello world 0, hello world 1, hello world 2, and so on, up to hello world 499. That's all this program does. It's written in a C language that humans, we can see and understand this. But if you actually compile this program and then get the binary and usually run it on the hardware, whatever the hardware is, if you run it on a phone or a laptop, a desktop, whatever it is, then it looks something like this. I've chosen that the hardware is an Intel CPU. If it was an Intel CPU, it looks something like this. It looks cryptic with all these numbers and these cryptic words. What are these? These are what we call as assembly language, or in other words, machine code, if you will. But this is essentially what the hardware sees, and this is what the hardware understands. So, I mean, a little bit of to understand, okay, how do I go from the picture on the left to the picture on the right? I think some of the colors in the picture help us understand that a little bit. Each line, you see a number and a colon and some an instruction, as we call it, on the side. These are just the addresses on the left, or the numbers on the left, or base 16 numbers or hexadecimal numbers, and that's where that particular instruction is. So the first instruction is a 1-byte instruction, so it starts at address 0, ends in address 1. The second instruction is a 3-byte instruction, and so on. And what those bytes mean it depends on the what it says. Push is a type of an instruction, move, sub, and so on. Sub, for instance, subtracts. These are the operations that the hardware does. And if you look at the green squares in 11 or 1, 1, and then you see 2 green squares. And what it is this instruction at address 2F is a JLE, which is actually a jump instruction. So what it does is jumps to the address 11. So once control flow comes to this particular portion, the hardware then jumps and to this instruction 11. So what happens when you actually take this program and run it on hardware is it's converted into these small instructions, and these instructions are fed to the computer or fed to the chip like how coal would be fed to a steam engine. One by one, the hardware fetches or picks up each instruction and then executes it one by one. And once it sees a loop, in this case, the JLE11 is a loop. It goes back and continues. This is exactly what we are doing here. This is a for loop on the left side. It's also in the assembly code, it's also a loop. If you see, there would be a blue color printf in here. A printf in this case is a function provided by the operating system. I mean, Windows or Linux or Android, whatever the Linux is the operating system in Android, this functionality is provided by the operating system with some wrappers. So this is actually a call or a function call to that particular function. So this is an equivalent translation of what we see at a high level. It's a loop essentially. And then you look at the pink 1.2b. It compares against the cryptic number. The cryptic number is 499 in decimal. So it compares to see if I have reached the limit of 499. And if I have, then I exit basically. So it's nothing but, what we're seeing here is nothing but a translation of the program on the left. It's as simple as that. Now, why did I show you this cryptic thing called as the instructions or instruction set? We have so many instruction sets. We have Intel CPUs understand this language called x86. This is the language that all Intel CPUs understand. AMD CPUs as well. They understand only this language. On the other hand, if you have an Android phone, they understand a different language, an ARM instruction set, and so on. So the instruction set architecture is the view that you get from above, from software, as to what the hardware does. So this is a first top-down view. And now let's go to the all the way down to the bottom-up view to look at what microarchitecture is. Microarchitecture is how the chip or the CPU is built. So take a bottom-up view of that. Let's begin from the beginning, right? Let's go to our high school physics. Just like my phone has mass. It has just like how mass is a fundamental property of matter. Charge is a fundamental property of matter. We all know that all elements or all molecules are built of atoms, and atoms are made of electrons and protons and neutrons. So electrons have a negative charge, protons have a positive charge. Charge is an inherent fundamental property of matter. And whenever there is flow of charge, and due to a potential difference, electricity flows, current flows. So materials, you can classify them into different kinds based on how well they can conduct electricity. They can be good conductors like copper and gold and aluminum and so on. And you have insulators or bad conductors like wood and maybe plastic and so on, rubber maybe. These are insulators. But there is this third class of materials called as semiconductors. What is this semiconductors? They're special materials that you can make them either conductors or insulators, depending on what input you provide. So they're really a special class for that reason. And the most popular semiconductor materials, they're all in the fourth, carbon group of the periodic table, with like 4 valence electrons. If you remember all our high school chemistry. So carbon, silicon, germanium, they're all in that field. So the silicon-based semiconductors that are the most popular, the way that is in the bottom. So all of the chips and so on are built from sand, and silicon is abundant material in sand, right? So essentially, you take sand and you make these semiconductors. How do you make these semiconductors? You take silicon and then you add some extra electrons. So if you add phosphorus to it, phosphorus has 5 electrons in the valence thing, or you have add some that have only 3 electrons or 1 deficient electron. Boron is a substance that has 3 electrons in its valence. So you mix them, add a little bit of those boron ions and phosphorus ions onto silicon, and you get, voila, you get what is called as a P-type material or an N-type material, and you connect them, that becomes what is called a diode. I mean, this is all stuff that you may already know, but I just wanted to refresh. You take a diode, a P-type, P-N diode, or you can create string 3 of these materials, a P-type material that has, that's doped with boron, an N-type material where silicon is doped with phosphorus, and you chain them, P and P together, you form what is called a transistor. And a transistor is a beautiful construct in that I mean, you can use it for very many things. And but in our topic, where we're talking about digital circuits are those that work with ones and zeros. Transistors are essentially switches, so you can turn them on or turn them off anytime, whenever you'd like. So these transistors are essentially what make up your chips today. So they can be used to build things like adders and multipliers and so on, or they can be used to store information as memory cells. So on the former case, we call it logic or compute, and the latter case, we call it memory. So this is how a chip is put together. It all comes from transistors and semiconductors and transistors. I mean, essentially transistors. So, I mean, a conceptual view of what a chip is essentially a processor and memory. Whether it has one processor or many, or one memory or many, the structure of most digital chips that are programmable have this particular form, where you have a processor and you have memory. The programs reside in the memory. The processor takes that program and executes instructions one by one, writes data onto the memory back again. So all the inputs and outputs go back to the memory. So this is the structure of a microarchitecture to begin with. All right, we have 3 minutes or so. So maybe I should pause here, and then we can continue this discussion. Looks like I may have time only to talk about this in the next session as well, but that's okay. The point here is to try and reach the students, not so much cover material. So let me stop here, and then see if you have any thoughts or questions. No questions. Is it so? Maybe is it all too elementary? Maybe should I pop up a level?
Actually, if it's okay, I can ask a question. I've got curious.
Please, KG. Absolutely.
What is the physical or the fundamental element in the bottom-up approach that tells you the transfer of things between memory and processor?
So let me try to understand. So when you say what is, so what are you asking what is the fundamental part of this this bus that connects the memory and the processor? Is that what you're asking?
Yeah, what tells
Okay.
to say, okay, take this memory, push it to processor to run it in this sequence?
So memory is a chip also. It's a chip made up of all these silicon-based semiconductors. Processor is another chip, another semiconductors. This arrow that's in between is actually what we call as a bus, is a bunch of wires, really. It's a bunch of copper wires there that connect the silicon in the memory to the silicon in the processor. So this arrow is not even a semiconductor, it's purely a good conductor. It's copper wires, actually. Does that answer the question, KG?
I think I got understood now, but like I got the pointer to it. But so you're saying there is something in the memory that tells to push something out to processor.
Correct.
And it's done in a way that.
So you're asking how the processor reads those instructions, or what tells the processor to get going?
Yes, yes.
Okay. So there is, I mean, all of these, the processor has a lot of, apart from the signals that, I mean, memory and the data and so on, the voltage supply. for any circuit has voltage supplied. So there is actually, I'm not showing the connections to the battery or to the your power supply. So there are signals, control signals. Your reset button in the computer, for instance, kickstarts the processor. So when it's an actual chip, signal starts the processor, and then once the processor is reset or starts, it is in this infinite loop. Always the CPU runs this special purpose infinite loop, which is there is a fixed location in the memory that it goes to and starts fetching instructions. So it basically pulls instructions in. Memory does not push instructions in. The processor pulls instructions in.
Yep. Thanks.
We are on the top of the hour. Either it's been extremely clear or it's been extremely useless. Which one of it is it? Please share. Did you get something from the at least the discussion today, the session today? How would you like me to cover the next session? I could go pop up if this is all material that you already know. I can go deeper or go faster or stay at the same pace. What would you like? Because the point here is really to reach you guys.
Sir, even though this is something a little familiar to many of us, I feel like it was good to have a kind of a refresh to these concepts. So I think the pace you're going in currently is fine with me.
Okay. Let's thank you for that feedback, Abhinand. I think
Karthik, do you want me to
Vishnupriya.
Create a poll and maybe have everyone else also answered?
Oh, that would be great if you could help with that.
So
Vishnupriya.
I'll just launch a poll and maybe everyone can just answer it.
Sure. Yeah. For the next session, how would we?
Yes. So we have 3 of them who have answered the poll. It'll be great if every one of you could answer.
Sorry, I'm being more enthusiastic today than ever.
Absolutely, KG. Thank you. I would love for questions.
So as a this sort of a program, I'm looking in terms of the tension computing. I want to get a feel of say 10 years, 20, 30, 40 years from now, how it would look like. Starting out, I'm sure you'll say it's going to be hard to predict, but at least there should be some pointers today.
So, 40 is too long. 40 is just the last 40 years have been like a million-fold changes, right? So 40 is too long, really. But 10 years is where usually visibility is for anything, actually. And there we do see that we hear a lot about quantum computing, for instance, or Moore's law even slowing down and so on. So we'll cover some of that the next time as well. But how this is going to go, if you're asking my individual opinion, and I believe transistors will continue to shrink and will continue to make innovation. I see an explosion of collaboration happening. I will share that towards the end of the next session as well. But I see an explosion of hardware design that everybody does. Previously, it was the purview of a few companies. Now everybody is doing that. There is hardware is learning from the software world in creating open source software and very agile and quick design methodologies. So, I mean, it's all exciting time for architecture, computer architecture. In fact, in the relevant section site, there is the ISCA 2018 lecture where the professor David Patterson and John Hennessy, who are the authors of a very iconic textbook in the field, right? They talk about golden age of computer architecture, because everything else, I mean, free performance improvements, times done. At the same time, the laws of physics are the same for everybody. So, I mean, there is the challenges of power, thermals, and so on is always a constraint that any system will work around. So the near term is what we can see, which is in the next 10-ish years, not 40, but hopefully that answers gives you a general perspective. We will talk about those trends. We will talk about what has happened in the last 40 years in terms of architecture, and provide a little bit of a preview to what I believe is maybe the next few years.
Thank you.
Thank you. All right, we are 5 minutes past, so let's stop. I look forward to a more engaged discussion next time, hopefully. Oh, we have the poll already.
Yes.
A third think it's elementary. 2/3 think it's the right level. Okay, I mean, if you believe this is where we are, I think we should be okay, because then at least the next few set of topics we will go into a little bit more of architecture. So pipelining and out of order processing and so on, CPUs, GPUs, multi-cores, and so on. So I think it should be at the right level. All right, thank you for that feedback. I will stop sharing. And thank you, Vishnupriya. If Professor Mala is here, thank you, Professor Mala. And thank you all students for joining. Let's connect again on Monday. And if you could stop recording, that's great, Vishnupriya. Thank you.